over to you and take it away.
Thank you very much, Darby, for this introduction and for managing these COINFLIPS seminars, which I try to very closely follow, and what you guys are doing, your activities. I think it's all great. It's great to be speaking to this crowd. So today I'll try to tell you a little bit about our work in this area that we've been calling probabilistic computing with p-bits. And it's been a few years now, and I think it's at a very exciting stage with input from various levels of the abstraction. So so this is my team and collaborators. A lot of the initial ideas in this space we've developed with Professor Supriyo Datta from Purdue University. So and he still is a important person that influences our thinking here in what we do now. And I have some collaborators. I work with Professor Hideo Ono, Fukami, and Kanai on getting these. I'll tell you a little bit about these nano devices, and then the rest are my students. And then there's Professor Giovanni Finocchio, who I also collaborate with. So let me get started by saying a few words on where we are today in computing. And you can think of it. I'm sure everybody has heard of bits and qubits, and bits, of course. They basically enable our modern life. Everything we do is by this amazing technology that we've developed over the last 75, 80 years. And you see, I think, I don't know the latest number, but I've heard recently it's 150 billion transistors on chip now. It's really staggering what's happening there. And in some sense, this is a spectrum, and on the other end of the spectrum, from classical to quantum, you have qubits. And qubits, as I always say that, even to define it, you need to introduce this technical term that you have to say it's a superposition of 0 and 1, and you have to get into discussions of what exactly that means, etc. But it's this very different object from the bit, which is deterministic 0 or 1. And there's this giant effort, worldwide effort going on currently from a lot of companies, universities, trying to build these quantum computers to use for some useful computation. Now, the thing that's interesting is that both of these things, both qubits and bits, are becoming domain specific. That seems to be a very common theme in this new era of electronics at the end of Moore's law. We're seeing the emergence of XPUs, where X is another letter of the alphabet. It's either a GPU, TPU, NPU. But the key point is you're developing these chips for some specific application. And the same is true for quantum bits. I think most people would agree that quantum bits are not to replace everything, but they are going to help you with specific things. So we've been, our story with this started by trying to understand qubits, that, okay, what makes qubits very useful or very different? And along the way, with Supriyo, with Professor Datta, that we've, come up with, this word that, and we are often surprised how this wasn't invented or defined before, because it's really a natural thing to define. As you take a bit and try to go to a qubit, in a hardware, in an implementation, at some point you're going to pass through the p-bit. You're going to have to be probabilistic before you can be quantum. So the key point is that the p-bit is not phase coherent or a substitute for the qubit, but it's not classical either. We want it to fluctuate between 0 and 1. We want it to have inherent noise at the very core of this abstraction. And that's also domain specific. It's not to replace, you wouldn't want to replace this with deterministic computing that you use in an airplane or in a flight control or your bank account, right? So this is good for certain applications where randomness is really fundamental or really important. And machine learning seems to be full of that. In fact, a lot of problems in machine learning are naturally probabilistic. And I'd like to argue with examples today that even this application space of noisy intermediate scale quantum era, this era that defined for where we are in quantum computing today, it looks like p-bits eat a lot of, or at least can overlap. The applications can overlap, and maybe p-bits can be useful for those as well. So what are these applications? Well, this group, the COINFLIPS group, is very familiar with, for example, massively parallel true random number generation, a very important application. If you need a massive amount of random numbers, maybe you could use p-bits with enormous throughput in hardware to do this. And in machine learning, there is this class of energy-based or generative models. And sometimes these are Boltzmann machines, belief networks, equilibrium propagation, a lot of statistical physics inspired models. And what we've seen is a lot of those models have directly what we describe as a p-bit, the abstraction. They directly fit these models that could be accelerated and built in hardware. Now, the other thing that's becoming very popular, and there's now a DARPA program, and there's this huge interest in solving computationally hard optimization problems, usually discrete combinatorial problems, things like maximum satisfiability, integer factorization, knapsack, and other things. And there the idea is you define an energy landscape, once again, a physics-based idea, and then you try to find these high quality, low energy solutions over this very big space of this discrete combinatorial possibilities. And finally, maybe less well known, but I'm sure it's going to be more and more common in our field, in this field of unconventional computing and people who are looking at probabilistic computing, quantum simulation. A lot of it you can do it with probabilistic computing. Now, this isn't a controversial statement at all, but I feel that it's not often talked about or widely appreciated. And there's this two ways. One of them is old and the other is new. The old method is the so-called field of quantum Monte Carlo. That almost sounds like an oxymoron, right? Like, how can you be quantum by just probability? But it turns out this is an old idea known to physicists, that you can take a quantum network, a qubit network, and then have replicas of it. And then you can replace the qubits with p-bits and have the replicas interact. And this is a faithful mapping to a lot of the properties of that quantum network. And this is only limited to certain problems. So it's not, and you can't do this for everything. I mean, it's not efficient for everything, but a lot of things you can get away with it. And QMC is an important field that people still use to estimate quantum properties, because quantum computers are not here yet to do that for you. The other thing that just came out maybe in the last few years is this idea of, you know, how they say machine learning eats everything, right? So this is the idea of throwing machine learning at the problem, saying that I'm not trying to emulate the qubit. It's a probability distribution at the end of the day, right? So I'm going to learn it by a Boltzmann machine, by an energy-based machine learning model, for example. So once again, we see that the p-bits could play an important role there, and we have initial results that does things like that. Okay, so and there are many more applications. So I just, this is just a sort of crib sheet of things that you could do, but I hope that, we deeply believe that there's a lot of applications that could be important. Okay, so let me now get into it a little bit let me define what we mean by a p-bit. We have an analog. We always think of a hardware abstraction. We imagine there's something in hardware that you build, and it has an analog or continuous input, a tuning parameter, and then a digital output or a binary output. And the way it works is, if you're a mathematician, this is a Bernoulli variable where you change the probability by an input parameter. Okay, so, if you're not a mathematician, it's like you have a bit string, you have a very noisy oscillator that goes 0 and 1 as a function of time, and you can change the duty cycle of that very noisy oscillator with this input parameter. Okay, and if you sit and take averages, you'll see that the way we design it, we design that average to follow this familiar sigmoidal or hyperbolic tangent curve. And the reason we do that is that we want this to simulate a physical system, and physical systems often have that exponential relationship, and that's related to this hyperbolic tangent. Now, so that's really it. And the p-bit works with this binary. And so in machine learning community, this is known as this binary stochastic neuron, that every update is stochastic, and then it's binary, and it's a neuron because it's doing something like an activation. Now, there's lots of, just like you can build bits and qubits with many different physical realizations, there's a lot of ways that you can build a p-bit, and I've been interested and been doing this magnetic tunnel junction based p-bits, but others have, I think by now there are a lot of competing ideas, diodes, RRAM and FETs, ferroelectricity, etc. But the other thing is you can also do this with CMOS, digital CMOS, which I'll tell you in a little while. And you can probably do it with creative analog designs in CMOS as well. So lots of different ways. To me, I'm a proponent of MTJs, but I always think that if there's a better p-bit, that would make everything better. So we are also a little bit agnostic to what the best p-bit should be. So let me give you an architecture. So the architecture is, so the anatomy of a picobit looks something like this. You have a really asynchronous system where you have your neighbors, the p-bits, that are defined over a graph. For example, you may be someone who has, let's say, 5 or 6 friends, and then you're taking their input, these binary inputs, and then you're summing them up, and then you're making a decision based on that sum. And the thing is, the clocks, as you can see here, can tolerate a lot of variation. It doesn't need to be synchronized. It's just like a physical system. You let it go, and then they evolve. And of course, there's feedback because p-bit I could be influencing some of these neighbors, right? So this is there's a solid math behind this. This is called Markov chain Monte Carlo. I'll explain to you in a second. This is technically called Gibbs sampling. And the basic idea is you have a dynamical system that evolves as a function of time. That's the MIs and I sub i's that you see on the picture on the right. And they try to approximate this Boltzmann law. They try to approximate this ground truth with 2 to the n states, and they try to emphasize these low energy states or high probability states. Okay, so here I'd like to mention that this is actually a family of algorithms. You don't have to, because we've made a choice over the energy function here. This is called the Ising model, but in truth, it doesn't have to be the Ising model. In truth, it could involve things like generalized Ising models, where instead of just Ji, J, Mi, Mj, you could have a cost function or an energy that goes Mi, Mj, Mk, or even higher. And in that case, the architecture would not change at all. The only thing that would change is you would have to do this in this gray box. Now you would have to add or make a more complicated addition and or multiplication. And that's really simple and efficient in p-bits because they're binary. So you're not really multiplying. You're really multiplexing. You're either getting the weight or not getting the weight. And that's a tremendous simplification. So that means these more powerful models could also be implemented in hardware. And these are typically very, very difficult in software. The things get very complicated very quick. So let me show you the main motivation behind this. So the main motivation is really trying to do this efficient MCMC, Markov chain Monte Carlo. And the way it works is, if you have 2 p-bits, you have 4 states, up, 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 down, down, up, and down, down, right? And if you have 4 p-bits, you have 16 states, because now there are 16 combinations. And pretty soon, you see that you do these histograms, and it looks like a nice skyline of Chicago, for example. And pretty soon, it's no fun drawing these histograms because there's an exponential behind it. There are too many states, right? And this is an idea. So the p-computing idea is to build something in hardware that samples from this enormous space as a function of time and gets you those probabilities, estimates these low energy or high probability states efficiently. That's what you want. And this is an idea, and in physics, those probabilities are usually related to this exponential of a minus energy. Energy is a cost that's given by that state, etc. Right? So this idea, interestingly enough, was proposed first by Feynman, and Feynman is credited by starting quantum computing. But he says in that very talk, simulating physics with computers, he says, if you're trying to simulate a probabilistic nature, maybe it's a good idea to build a probabilistic computer, and that's really the core of what inspires the core of what we do. And let me tell you that in physics, a lot of these problems in many-body physics is really emanating from this 2 to the n, this exponential. And there's a lot of approximate methods physicists have developed over the last 50, 60 years. And some of them are like powerful models like mean field theory, loopy belief propagation. But in our experience, nothing beats MCMC. Okay, so nothing beats actually building this as a system and then evolving it and trying to sample from those states. So since this is such a central algorithm, accelerating it or building hardware to do this very important function seems to be a good enough motivation. Okay, so the idea is sometimes, here's a visual of what I have in mind with when I say like build this in hardware. So imagine a box of molecules that are interacting. And, this is a picture that we've all seen in, statistical physics and things like that. And how does this work? What are some salient features of something like this? Well, first of all, things are local. If you check what's happening in this left corner, you'll see that this object, this body, is only interacting with local neighbors around it. So things are sparse in nature. Things are not non-local. And secondly, there is no clock. As computer engineers, computer scientists, you're thinking of clocks all the time to synchronize. You cannot imagine a CPU without a clock. Well, maybe some of you, maybe Rajit Manohar can, but in general, we have a lot of clocks in our circuits. But in nature, there is no such thing, right? So in nature, everything is asynchronous. And a corollary of that is everything happens at the same time. What that means is if you double the system size, the interactions, its throughput will also double. So this is what we try to do with p-bit. All three of these features, we put them in our circuits. They're locally connected, asynchronous, and they are massively parallel. You can measure the number of flips taken, for example, by your machine. That doubles when we double the size of the system because things are local. So, okay, with that sort of general introduction of what we're doing, let me now show you what we did in hardware, some of the things that we've implemented over the years. So a couple years ago, we implemented this prototype 8 p-bit computer where we were using, I'm going to show you what these are. This is a nano device, a stochastic magnetic tunnel junction that was generating noise on its own. And then this is exactly the same architecture I showed you. Remember that feedback that you get from your neighbors. And in this thing, we did this feedback by a microcontroller, okay? And we've solved this generic optimization problem where we saw that, okay, if they're uncorrelated, they sample from the uniform distribution. And then when they get correlated, they find these low energy or high probability states on their own, right? So that showed this asynchronous, locally connected nature of this problem. And, I often say that this took me maybe, I was part of this team. It took us, 3-4 years to get here because these nano devices are so difficult, etc. But then we wanted to do this with FPGAs. Why don't we scale this system up and pay the price of this random number generators, which are very expensive. But in 2022, we did this 5,000 p-bit FPGA. And it's really ironic because now you're using billions of transistors to put 5,000 p-bits in it. But nonetheless, we solved, again, a similar generic optimization problem, this integer factoring problem. And we saw, okay, we could factor much larger numbers than anybody else who is using similar probabilistic methods. So we started to grow into this architecture, this asynchronous sparse architecture that we've used. Okay, and there's some comparisons with D-Wave, etc. I'll show you later. And recently, we've been trying to combine, to introduce ideas of heterogeneous computing, where, okay, if randomness is expensive, maybe I can provide it from the outside to a digital platform. And maybe one day these could even be monolithic on top of each other on a CMOS chip. But here we did this on a PCB level, and we showed that, okay, you can have an SMTJ or this nano device that gives you random noise to drive a large digital system. So going towards these heterogeneous solutions that one may define. And in fact, we've been recently scaling that up. Now, instead of, previously in last year's IEDM, it was like, okay, one MTJ feeding this big, large circuit. It's a proof of concept. Now we've done it for 5 MTJ. So you're kind of, it's still a small thing. It's still nothing that you can't do with a normal digital FPGA, but you are able to study these stochastic dynamics and you can explore these heterogeneous ideas. And the idea, as always, is you define an energy function that becomes a graph. That graph goes into the hardware, and then you try to sample from it using your qubit architecture. Now, I'd like to, talk about, somewhat tongue-in-cheek, the probabilistic advantage or supremacy. So the key point is, can you do something with a probabilistic computer that is simply not doable in terms of energy or performance by anything else, classical or quantum? And in our part, for example, a subversion of that question is, could you have an SMTJ FPGA combination that could beat an all-digital FPGA adversary, for example? That itself would be very interesting, because FPGAs, as we know, are very, very powerful, right? So this is, one of the things that we are trying to think about is, can you define something that is this probabilistic advantage, that's something that can't be done by anything else? And we are trying to scale this up to 100 MTJs, etc. And one thing that I want to emphasize, which is really the focus of this program that you guys have, is the crucial need for algorithm and hardware co-design. We see that if you just focus on the hardware or the algorithm, that really doesn't work, and we have to be constantly aware of all the all these algorithms and that fits to our hardware, right? Okay, so we have skips, beyond just doing MTJs feeding digital things, we are also desperately trying to simulate or emulate these p-bits. One thing, because we are basically, we used up all the FPGA, even you use the world's best FPGA and we used it up, so we are trying to take a graph, split it into 4 pieces, minimize the connections between them, and then have a distributed FPGA platform that maybe you can go to 100,000 or 250,000 p-bits on chip, that they're all working on in parallel without any multiplexing, for example. And then we have a lot of problems that we'd like to try on these machines. So we are really trying our best, not just from a nano device sense, but pushing the limits of what we can do. And as I always, I sometimes remark that as I've worked with FPGAs more, my respect for the nano device and the physicists have increased dramatically, because of how difficult it is to put a lot of random number generators in these digital chips. So that's why I'd like to tell you, this magnetic tunnel junction technology a little bit in the next few slides now, where maybe you can have a 1 million p-bit on chip, and maybe you can distribute it into 10 million p-bits in distributed architectures like this. And the point is, if you accelerate an important enough function like MCNC, that could be useful for a whole host of applications, and that could be like a GPU, TPU like success story. Of course, these are speculative ideas. So now let me tell you a little bit about this magnetic tunnel junction based p-bits. And so this is the function we want. We want this tunable randomness that's binary and with a continuous input and a digital output. And one way is one thing you can look at is physics and physics of magnetism. Those of you who are familiar will know that in order to store a bit to a magnet, what you do is you have these 2 states, red and blue. You have a 2-state system, and then you separate those red-blue states by something like 40 kT or so. And then the idea, what they will tell you, like experts like Andy Kent, for example, they will tell you that, look, this retention time will be an exponential in the energy barrier that you've designed. And you multiply that with some number that's a material dependent picosecond to nanosecond number, and you can do the math, like exponential of a 40 times a picosecond or a nanosecond, that gives you some number of years. And in fact, they try very hard in magnetism to make these as small as possible, but to keep the energy as high as possible. That's in fact their main challenge in order to scale these things up. Now, what we want is, of course, the exact opposite. You want it to be as bad a memory as possible. So you want to remove the energy barrier as small as possible. So that's going the other way. And if this formula doesn't work, if you're an expert and you see this formula is not exact anymore because there is no notion of a 2-state anymore as you reduce the delta. But just as a basic exercise, you can see that can look like picoseconds to nanoseconds, because exponential of a 1 could be just a very small number, right? So this is how our collaborators from Tohoku University design these magnetic tunnel junctions, a nano device, a two-state nano device where you have usually a fixed layer and a free layer, and then the idea is, if the reference if the configuration is in this anti-parallel state, then you get a high resistance, and if it's in the parallel state, you get a low resistance. And usually, these are only if you're coming from the CMOS world, this on-off ratio is horrible, really. It's like 2 or 3, and that's why they report their percentages in hundreds. They said it's 600%. It's really an on-off ratio of 5 or 4 or something like that. Okay, but the key point is, you can sort of make one of those free layers a stochastic paramagnet, and what happens is, as a function of time, you can see this fluctuation in the resistance. And to me, this is really a strange thing to see in the lab, that you can take a 2-terminal resistor, look at it, and it's changing its resistance from 10 kilo ohms to 20 kilo ohms, for example. You're not doing anything. That's just giving you a random bit string for free. And a few years ago, we were doing the theory on this, and it wasn't at all clear that these magnets could be very fast. But recently, there are some experimental developments that actually showed that these things can be very, very fast. And I'll show you that in a second. Now, of course, this is very good. You have a random bit string, but that's on the resistance. You still need to put it together as an electrical circuit. And to do that, we looked at this STT MRAM cell, which is this 1 transistor, 1 MTJ cell. People do memory devices with these. And, TSMC, Samsung, Global Foundries, and others have scaled this technology up to billion bits now. So we're talking about a scale technology. There's already CMOS plus MTJ chips with an enormous number of MTJs on them, but they want memory. So what we want is slightly different. We want P bits. So the way to modify that cell is, what you do is, okay, first you change the stable MTJ with an unstable one, and you keep the transistor, and then you add an inverter. Okay, so it's just 2 transistors here. So there's a 3 transistor, 1 MTJ cell, and you can do a lot of careful simulation with BSIM models, with magnet models, LLGs, and so on. And you can see that you roughly get, as a function of this input voltage and the output, you roughly get what you want in this ideal behavioral equation. This can look better depending on the MTJ design, the TMR, etc. There's a lot of details there, but okay, that kind of gets you what you want. And let me now tell you some of the recent developments. We did this experimentally, as I showed you earlier, in 2019, but those were very slow MTJs. And at that point, it wasn't clear whether these could be fast. And in 2021, an experiment from IBM, they showed this demonstration of nanosecond fluctuations in stochastic magnetic tunnel junctions. It's a very big, important development. At the same time, nearly at the same time, a Tohoku group, Fukami and Ono, they've done the same, nanosecond telegraph noise in plane magnetic tunnel junctions. And now I think this has become a routine experiment. I just saw this paper from another group. Now they're also doing nanosecond through random number generation with these SMTJs. So it is clear that these devices can be extremely fast. You can get 1 billion numbers every second. And I'll tell you in a second why we need an enormous amount of random numbers when we saw the real example. So this is from our group. Nanosecond fluctuations have been demonstrated, but these are all doing it on a well-controlled lab in a sort of probe stations around. What we did was we took these fast fluctuations from Ono and Fukami from Japan. And recently we've put together an electrical p-bit. So here at the bottom, you're seeing an electrical fluctuation based on these p-bits, and they're now at microseconds. Okay, so they could be very, very fast. Okay, and this is now electrically done, and we're going to talk about it this year in IEBM. Okay, so that's how you basically can make these SMTJs. But now let me switch gears and show you a little bit of a few examples on how the system works. How, if you scale this, okay, why should we spend all this time to do device research? So let me show you why that might be worthwhile. So now I'm going to show you an example on hard optimization. Okay, so in particular, I'm going to talk about this integer factorization. And the way we're going to do it is we're going to write the integer factorization problem as a circuit sat problem, as a circuit satisfiability. If you don't know what that means, it's very, very simple. Okay, you basically write down a school book multiplier. So how do we all multiply? You take two integers. You multiply their digits individually. So there's a bunch of AND gates, right? And then you add them. You basically shift them and add them. And these FAs that you see here are just full adders that does the addition. So this is really nothing but this school book multiplication that all of us know, right? So this circuit, there's one catch though, that you make the circuit with P bits. So they are probabilistic AND gates and probabilistic full adders. And when you have a probabilistic AND gate and a probabilistic full adder, what you can do is you can ask these normally silly questions like, okay, what if I fix the output bits to some value and ask the circuit to give me something that satisfies that output? Okay, so that's, this is a very different way of doing Boolean logic, and we call it this invertible Boolean logic, that you can write down this digital multiplier circuit and ask your circuit, okay, I'm going to fix your input output to 6. What input combination gives me 6? And the circuit, it will search and it will find the satisfying inputs, 2 and 3 or 3 and 2. And that's why we call it the circuit satisfiability. Okay, it's a problem space and it's a problem in computer science. Now that circuit could look like a simple thing, but if you do it with p-bits, that becomes this enormous graph. Okay, so this is an example of integer factoring. It's 3,400 p-bits. And remember the problem that you're facing. Why is this a difficult problem? Well, you have this exponential space. So the possibilities for this network to attain is 2 raised to the power 3,400. Enormous phase space, okay? And then you build this circuit in hardware, and then you try to put the best annealing algorithm on it, which happens to be this parallel tempering algorithm. I can tell you a little bit about it, and then you try to reduce the energy, and some 123 trillion random numbers, you get to the ground state. Okay, and this is a very difficult problem. This is a 40-bit factorization written as a circuit sat problem. Okay, and again, I told you earlier that we could do 32-bit. Now with better algorithms, with algorithm hardware co-design, we can now go to 40 bits. Okay, and so that's very good compared to others who are solving it in the same way. But let me tell you that this, to me, is integer factorization is a very special problem because there's a good quantum algorithm for it. But here, it is a very difficult benchmark for us. This clearly isn't scaling. I mean, for example, 40-bit is not a large number when it comes to factoring. From a probabilistic spin glass point of view, it's mind-boggling because you have 20 p-bits, 2 to the n states, and you only have 2 ground states, and you're trying to find one of them. You see, it's very difficult, but there are other better algorithms for this. For us, this just shows us how our circuit can do generic optimization. And the more important thing is, in 200 seconds, our FPGAs today can take 123 trillion random numbers. So this is why when sometimes I talk about this thing, people often say that, oh, I have random numbers. Random numbers are not difficult. Yeah, but I need 123 trillion in 200 seconds, and they should be uncorrelated. Could you get that to me? Right, and this puts a lot of limits and sort of constraints on what you do with your pseudo-random number generators and so on, right? I mean, they have to have a decent period and so on and so forth. So that's the nano device angle. That's why we think the MTJ can play such an important role. Now, I'm nearing the end, so let me show you a few quick examples that I'm not going to go into huge detail. If you want, we can talk about them. Beyond combinatorial optimization, some problems, okay? And specifically, as I mentioned, is energy-based ML models. So the way this can work is, in these generative machine learning models, usually this estimating or generating samples from a pre-described distribution is one of the most difficult things. Because as I said, again, you're trying to tackle this 2 to the n problem. So we are thinking of these hybrid schemes where you have a probabilistic computer that takes an enormous amount of samples every second. Let's say 100, you can take 100 billion samples every second. And then by taking a lot of samples, it can generate good quality, high quality outputs to you for your classical computer. And then your classical computer uses what comes from the probabilistic computer, and it gives back new weights after computing a gradient. So in this sort of feedback loop, you can go and train these some of these energy-based models. Okay, and we use, as I mentioned to you in the beginning, we really like hardware-aware sparse graphs. So these are two graphs that we used from the D-Wave literature. You know, D-Wave, they've been at this game of doing quantum hardware for similar, you know, with similar physics-inspired architectures, and they've developed these very nice hardware-aware graphs. Okay, so the one on the left is called Pegasus. I guess it looks like a bird if you look from the diagonal. And then the one on the right is called the Zephyr graph. Okay, so these are all sparse graphs, and you can load them, build them in hardware. You can lay them out in ASIC chips, etc. They have very useful properties from a hardware perspective. So we train, usually in Boltzmann machines and energy-based machine learning, models are all-to-all. If you talk to Jeffrey Hinton, sparsity wouldn't be on top of his list for coming from a hardware perspective. He would be like, okay, I'll have 2 layers, everything will be connected to everything. But for us, this is a very big difficulty. So we find that the study of sparse Boltzmann machines in this form is understudied. In fact, we can give you a lot of depth, but we can't give you a lot of all-to-all connections. And the results are interesting when you compare these things. If you compare an all-to-all connected Boltzmann machine and what you can do with a few layer deep sparse Boltzmann machine, the one that I talk about here, we see something very strange. We see that, you know, we can have 30,000 parameters and learn the MNIST data set up to, let's say, 90% accuracy. And in order to get to the same accuracy, you need 3 million parameters from this fully connected Boltzmann machine. And I guess in some sense, this wouldn't be, you know, hugely surprising, because in machine learning, we now understand depth gives you a lot of sort of representational power. So this network is a few more layers deep, and this network is only 1 layer deep. So that's why you can get by with much fewer parameters than requiring this all-to-all connection, right? And we can generate images with this sparse DBM, whereas the RBM cannot. So it's very interesting. Okay, you can look at some of these old machine learning algorithms and maybe find that change established wisdom that, you know, some of these things could be very powerful, enabled by powerful hardware. And the only reason we could train these things was because we had this very fast probabilistic sampler. You can't do this on a CPU without very special tricks and without waiting for a very long amount of time. So that's one example, and the details are in that paper. Now let me show you this again, this idea of learning quantum systems. Okay, for example, suppose you have a 1D quantum magnet. Okay, physicists study these quantum magnets all the time. You have these spins, now they're quantum mechanical, and you write this Hamiltonian, and now things are even more difficult, because previously I just had a scalar energy that required 2 to the n connections. Now I require a matrix. I need to diagonalize a 2 to the n by 2 to the n matrix. This is in fact the central problem in many-body quantum physics. How do you diagonalize that huge object? How do you tackle it? Right? And one way, of course, is to build a quantum computer, and look what it does. Look at what it does. And another way I mentioned is that you build a energy-based model, and then you have a variational guess. You say that, okay, I guess that this RBM can represent that the many-body distribution that is defined by that quantum Hamiltonian. And then you put it on a p-bit network, which has to be sparse, because this is, of course, a dense one. So we do that step. There are methods developed by D-Wave and others to take a dense network and put it as a sparse network. And then we solve this problem. Okay, we have actually, there's a paper on this. We just came out. I forgot to change this. If you're interested, I can show you. And the main point is, as a function of number of iterations, you can find the ground state of a quantum magnet like that. So once again, you know, when I talk to quantum physicists, some of these people tell me that this has become the state-of-the-art method in trying to estimate ground states. And they become very interested when you say that you can accelerate some of these things in hardware. Okay, so the point is that there's all these applications that could benefit from us having, altogether, us having from physics to systems, these very fast and CFC samplers that could be useful for these applications. Before I finish, I want to show you some benchmarks, okay, some concrete benchmarks. And as I said, I've been showing these quantum computer examples from D-Wave and so on, but, not to offend anybody, but they're not, they're intellectually interesting, but we shouldn't bully a, weak target, or we shouldn't compare us to something that's, easily beatable and then declare victory, right? The real competition is bits. The real competition, as I'll show you, is the GPU and the TPU, not the quantum computer. So, okay, so the device level comparison. I've been talking about this p-bit, this MTJ-based thing, random number generator, etc. What would a good, let's say, graduate student in digital design do if I show them that this is the abstraction I want? They would go and they would say, okay, I can do that in an FPGA. Well, I need a PRNG, a pseudo-random number generator. I can use the cheapest pseudo-random number generator money can buy, which is the linear feedback shift register. And then a more sophisticated one, which is called XOR shift and rotate. Okay, so this Zoshiro is more expensive. And then if you want tunability, I'll probably tune it by some lookup table and have a tangent hyperbolic. By the way, this is how we build our digital p-bits. So if there's a better way to do this, we would be the first users. We also care about how you build these things efficiently. But the fact is, if you just look at the transistor count for a 32-bit RNG, this LFSR, the cheapest random number generator money can buy, is just the PRNG is 1100 transistors for a 32-bit RNG. And these are real synthesized results from PDKs. So that's why I'm comfortably reporting 1122 and not 23. But if you want tunability, that becomes 5,000 p-bits. And if you're solving a machine learning problem, you quickly realize that this low quality RNG is not good. In fact, it fails you all the time. Okay, so you want a Zoshiro now, okay, but Zoshiro just became 7,500 transistors just for the PRNG and 1,100 transistors if you want the tunability. So it's an enormous difference. It's very, very expensive. Whereas we are doing this literally with a few transistors and an MTJ, and that can generate these gigahertz fluctuations if we design them right. So, 1 million p-bits, just the p-bits, just the PRNGs might require these 10 billion transistors. And that may not sound like a lot, but, considering where we are with transistors, you have to have the connectivity, multiply, accumulate, readout, IO, control circuitry. So there's no way that this is fitting. You're having a 10 million p-bit circuit in present day digital technology. And of course, there is anytime you have such an area penalty, you have an energy penalty. So if you want to measure the energy that it takes to create one random bit, that takes with the Zoshiro around 300 femtojoules, whereas you get basically like 150x improvements if you do it with an MTJ, because it's just so much smaller. Okay, so that's the device level comparison, and this is my final comparison as I wrap this up. So the system level comparison, and there a key quantity is this flips per second. How many times can you flip while talking to your neighbors, not randomly? So how many times can you do this intelligent flip with up-to-date information? So the thing is, as I mentioned to you, in the factoring problem, we required 123 trillion random numbers. So the bigger this metric is, the quicker your solution is going to be. So to me, this is a little bit like the clock frequency of a probabilistic sampler. Does it tell you how to solve any problem? No, but it tells you something. So it's a useful metric. So here's a chart where I'm showing you this flips per second in the x-axis. I call it sampling throughput. And then I'm showing you power consumption in the y-axis. Now, these are some results from NVIDIA and Google, and we have nothing to do with them. They're really trying to speed test their hardware on these Monte Carlo problems. And you can see that their powers are much larger. That's fine. Let's not worry about power for the moment. But even with sampling throughput, they're stuck around 10 flips per nanosecond or so. Okay. And in single TPU, single GPU type things. And they try all sorts of parallelism tricks. They use +1, -1 weights. Their graphs are simple, nearest neighbor, but they solve the same problem. Even with our FPGA today, it looks like we can get to 100 flips per nanosecond. So 100 billion flips every second. And then the energy can also be improved. But the key point is there's a lot of points between where we are, where things are, and where things could be. Because look at this P2 point. This is, of course, a projection. You know, it looks so good. It has to be a projection. But look at the number. It says 1 million flips per nanosecond. I just showed you that in the experiments, people have already seen nanosecond fluctuations. So 1 MTJ can fluctuate 1 MTJ can give you 1 flip per nanosecond. And they've already built this to billion-bit densities. If you have a million-bit MTJ computer, you can have 1 million flips per nanosecond. That's not out of the question. Okay, so that's what we think. Why we think speculatively that MRAM can take us our performance to stratosphere. So that's the end of my talk. Some conclusions. I talked about p-bits and p-computing. Maybe there's a notion of p-bit advantage. I guess that's the word to use these days. And lots of implementations from FPGA to CMOS to emerging nano devices. Okay, so with that, I'd like to conclude and thank you for your attention.